Advanced seismic wave analysis provides the primary evidence for this vast subterranean water inventory. When earthquakes generate shock waves that travel through Earth's interior, these seismic waves slow down significantly when they encounter water-bearing minerals in the mantle transition zone. The velocity reduction occurs because water molecules bound within high-pressure mineral structures alter the elastic properties of the rock, creating a detectable signature that seismologists can measure from monitoring stations worldwide. Global seismic networks detect these velocity anomalies consistently across different continental regions, confirming that water-rich minerals exist throughout the transition zone rather than in isolated pockets. The chemical process that allows water storage at these extreme depths operates through a mechanism unknown at Earth's surface. Under pressures exceeding 13 gigapascals, olivine transforms into ringwoodite, a mineral with a crystal structure that can accommodate substantial quantities of water within its atomic framework. Each ringwoodite crystal can contain up to 2.5% water by weight, incorporated as hydroxyl groups that replace silicon atoms in the mineral's tetrahedral structure. The water becomes chemically bound within the crystal lattice, remaining stable for billions of years despite the extreme temperature and pressure conditions. Laboratory experiments using diamond anvil cells demonstrate how water molecules become incorporated into these high-pressure mineral phases. When researchers subject olivine samples to mantle pressures in the presence of water, they observe the formation of ringwoodite crystals containing substantial hydroxyl concentrations. The transformation occurs gradually as pressure increases, with water molecules dissociating and recombining within the evolving crystal structure. X-ray diffraction analysis reveals that the water occupies specific crystallographic sites within the ringwoodite lattice, creating a stable storage mechanism that can persist for geological timescales. Volcanic eruptions provide the only direct samples of mantle minerals available for laboratory analysis. When magma rises from depths exceeding 200 kilometers, it carries fragments of mantle rock that preserve the chemical signatures of their deep earth origin. These xenoliths contain ringwoodite and wadsleyite crystals with water concentrations reaching 1,000 parts per million. Isotopic analysis of the water within these deep-source minerals reveals deuterium ratios matching the cosmic bombardment signature preserved in Earth's surface oceans, confirming that mantle water originated from the same asteroid impacts that filled the early oceans. The connection between surface and deep Earth water operates through plate tectonic processes that have recycled water between different reservoirs for billions of years. When oceanic plates subduct beneath continental margins, they carry seawater, altered minerals down into the mantle transition zone. The descending plates undergo metamorphic reactions under increasing pressure and temperature, transforming hydrated minerals into ringwoodite and wadsleyite that trap water within their crystal structures. Computer models calculate that subduction zones transport approximately 3 billion tons of water annually from the surface into the deep Earth, a process that has operated continuously since plate tectonics began. The deep water reservoir functions as a planetary thermostat, regulating ocean levels and climate stability over geological timescales. When surface temperatures increase due to enhanced volcanic activity or asteroid impacts, additional water evaporates from the oceans and eventually becomes incorporated into descending oceanic plates through hydrothermal alteration. This process removes water from the surface system and stores it in the deep Earth, preventing runaway greenhouse effects that could render the planet uninhabitable. Conversely, during ice ages when surface water becomes locked in continental glaciers, volcanic outgassing returns mantle stored water to the surface through eruptions, maintaining oceanic circulation and preventing complete freeze. The mantle water discovery explains how Earth maintains stable oceans despite major climate perturbations throughout its 4.5 billion year history. During the late heavy bombardment period, when massive asteroid impacts vaporized substantial portions of the early oceans, the deep Earth reservoir provided a buffer that prevented complete water loss to space. This planetary-scale water storage system has operated continuously for billions of years, preserving the cosmic inheritance delivered by ancient asteroid bombardment and maintaining the conditions necessary for life to flourish on Earth's surface. Yet Earth's success in retaining its water stands in stark contrast to other worlds that received similar cosmic deliveries but failed to preserve their aqueous inheritance. The same bombardment process that filled Earth's oceans operated throughout the inner solar system, delivering water to neighboring planets that today present dramatically different faces to the cosmos. Mars, the lost ocean world. Mars received the same cosmic inheritance as Earth. yet today presents a dramatically different face to the universe. In the rust-colored expanses of Jezero Crater, NASA's Perseverance rover extends its robotic arm toward a weathered boulder that has waited 4 billion years to tell its story. The six-wheeled Explorer carries within its chassis the most sophisticated analytical laboratory ever sent to another planet, equipped with spectrometers and imaging systems capable of reading the chemical history written in Martian rocks. Mission controllers at the Jet Propulsion Laboratory in Pasadena, California, watch their computer screens as data streams across the 200 million-mile gap between worlds, revealing secrets that reshape our understanding of the red planet's watery past. The rock samples analyzed by Perseverance contain mineral assemblages that form only in the presence of substantial liquid water over extended periods. Carbonate deposits within the crater floor preserve chemical signatures indicating that Jezero once held a lake larger than Lake Tahoe, fed by rivers that carved channels through the surrounding highlands. Advanced spectroscopic analysis reveals that this ancient water body persisted for millions of years, long enough for complex sedimentary processes to deposit layers of clay minerals and carbonates that record environmental conditions favorable to life. The rover's instruments detect sulfate minerals that precipitate from evaporating water bodies, providing direct evidence that Mars once possessed an ocean covering much of its northern hemisphere. This ancient sea stretched across the Vastitas Borealis region, containing more water than Earth's Arctic Ocean. The mineral evidence shows that this Martian ocean existed for hundreds of millions of years, connected to smaller seas and lakes through a network of rivers and deltas that rival those found on our own planet during its early history. Laboratory analysis of Martian meteorites that have fallen to Earth over millennia confirms that the red planet's ancient water originated from the same cosmic sources that filled Earth's oceans. The Allen Hills 8431 meteorite, discovered in Antarctica, contains trace amounts of water with deuterium to hydrogen ratios that match signatures found in carbonaceous asteroids. This isotopic fingerprint proves that Mars received its water inventory from the same population of asteroid impactors that bombarded the inner solar system during the late heavy bombardment period between 4.1 and 3.8 billion years ago. The chemical composition of hydrated minerals within Martian meteorites reveals that water played an active role in Mars geology for over 1 billion years after planetary formation. Phyllosilicate clays within the Nuclear meteorites show evidence of aqueous alteration that occurred within the first 500 million years of Mars history, when liquid water circulated through the planet's crust and chemically modified the original basaltic rocks. These alteration processes require not only the presence of liquid water, but also temperatures and pressures consistent with a thick atmosphere capable of maintaining surface water in liquid form. Computer climate models incorporating the latest understanding of early Mars atmospheric composition show that the planet maintained surface temperatures above freezing for more than 1 billion years. The models account for greenhouse gases produced by extensive volcanic activity during Mars' early history, when the Tharsis volcanic province was actively erupting and releasing carbon dioxide, water vapor, and sulfur compounds into the atmosphere. This enhanced greenhouse effect, combined with a denser atmosphere, created conditions that allow liquid water to exist across much of the planet's surface despite Mars' greater distance from the Sun. The key factor in Mars' water loss lies in the planet's fundamental physical characteristics compared to Earth. Mars possesses only 11% of Earth's mass and 38% of its surface gravity, resulting in a weaker magnetic field that shut down approximately 4.2 billion years ago. Without magnetic protection, the solar wind began stripping away the Martian atmosphere through a process called atmospheric sputtering, where high-energy particles from the Sun collide with atmospheric molecules and knock them into space. Earth's strong magnetic field deflects these particles, preserving our atmosphere and allowing liquid water to persist on the surface. NASA's MAVEN spacecraft, orbiting Mars since 2014, measures the ongoing atmospheric escape processes that continue removing water from the planet today. The spacecraft's instruments detect hydrogen and oxygen atoms escaping from the upper atmosphere at rates exceeding 100 grams per second, representing the dissociation products of water molecules broken apart by solar ultraviolet radiation. Isotopic analysis of this escaping atmosphere reveals progressive enrichment in deuterium over the past 3.5 billion years, as lighter hydrogen atoms escape more readily than their heavier counterparts, leaving behind an increasingly deuterium-rich reservoir. The Mars Reconnaissance Orbiter's ground-penetrating radar has mapped extensive deposits of subsurface water ice throughout the planet's mid-latitude regions. These buried glaciers contain an estimated 150 billion cubic meters of frozen water, representing only a tiny fraction of the planet's original water inventory. The ice deposits lie beneath thin layers of dust and rock that have protected them from sublimation over millions of years, preserving remnants of the ancient hydrosphere that once flowed across the Martian surface. Statistical analysis of atmospheric escape rates and isotopic evolution patterns allows scientists to calculate that Mars has lost approximately 99% of its original water inventory to space over the past 4 billion years. The planet began with enough water to cover its entire surface to a depth exceeding 100 meters, comparable to the water volume contained in Earth's Mediterranean Sea. This massive water loss occurred gradually as the weakening magnetic field allowed solar wind erosion to strip away both atmospheric gases and water vapor, transforming Mars from a potentially habitable world into the cold, dry desert we observe today. Mars serves as a planetary cautionary tale that reveals how subtle differences in size and magnetic field strength determine whether a world can retain its water over geological timescales. The planet's inability to maintain a protective magnetic field allowed the solar wind to gradually strip away its atmosphere and water, despite receiving its initial water inventory from the same cosmic bombardment that made Earth habitable. This comparison illuminates the delicate balance of factors required for long-term planetary habitability, where small differences in mass, magnetic field generation, and atmospheric composition determine whether a world remains a thriving water world, transforms into a frozen desert,